thanks to the organizers also for inviting me and giving this talk. So I say the first part will be I re-identify a little bit the basics of microscopy to start slowly. So about the conventional techniques of microscopy, I would say every microscopist should know. So just to go slowly, it's the beginning of the afternoon. Using lenses to improve vision, it's a very old technique. We have a text from a headline, the ancient, talking about emeralds, which were used as lenses. And the funny thing also, which is Thales, describing what probably are leaf cells observed through morning dew droplets. So they wonder what people were doing to observe through morning dew droplets in the morning. But the way it works. It has been a very long time then. We wanted to wait for 1,300 years to invent binoculars, which very rapidly became very popular throughout Europe. And obviously, then the idea of associating lenses through nature. There is a debate about the invention of the microscope by Zacharias Janssen, not 100% sure. The interesting thing is that guy is not a scientist. He's working in textile. At that time, single monocular lenses were not powerful enough because the progress of textile made the wires to be too small. So it really came, in fact, from a technological problem, not from science. Many people were building microscope because it was quite funny. It was really a curiosity. And Galileo is very famous for the telescope. In fact, also worked in microscope. And the book, which really started or launched the microscope as an optical tool, is this book from Robert Hooke. It is interesting from 2 points of view. First, it's one of the very first books which was not written in Latin. So this explains the diffusion of the book. And it is also in this book that one finds the very first mention of a cell, what a cell is a cell. And this really attracted the interest toward this instrument. So the progress were very rapid, except for the glass. The glass was really a problem making good quality glass, transparent. So one had to wait till the 19th century to get really good microscopes. And when I say good microscopes, this is a card-size microscope from the end of the 19th century. With such a microscope, not this objective, but a dedicated one, small details as small as 200 nanometers were visible. And the classical modern microscope, in fact, do not really perform better. But the ergonomy is better, of course, field of view is better, correction, color correction, but basically in terms of resolution, for example, it was not better. In fact, at the end of the 19th century in the history of science, it's an interesting phenomena. It's the first time that an instrument reached the theoretical limits before one used the theoretical limit. And because they could not make better microscope, card size, asked Ernst Haeberlé, who was working with Ernst Haeberlé already before, there should be a problem. We can publish, we can do whatever we want, no way to have better objectives. So Ernst Haeberlé, he was aware of the Fresnel diffraction theory. He applied the theory and came to this conclusion, famous Haeberlé law, if the resolution as a function of the wavelengths, lambda, divided by 2. This term, n sine alpha, is the numerical aperture of your objective, same limit. And we understand it's not possible to do better because, okay, sine alpha is 1. And that's the optical index of refraction. So for example, if you go from air 1 to oil 1.5, you get a factor 5, but that's all. You can diminish lambda, but of course, they will rapidly become too little. It's not very good for the cells. It's especially not very good for the cells. So many people were blocked. And then there was a kind of thing. Somebody as a company goes back to the university. No way to do better, but found many ways to do better images. This was to get better classes. In fact, the properties of staying. There were natural crystals available, but they were so difficult to find that what they did, they came back to shot from the shot glass. The company still exists, and saying, okay, we need special scientific classes. The interesting thing is more than 100 years later, there are two countries where still have the microscope objective manufacturers. That's Germany and Japan. These are the two countries who have companies making scientific glasses, shot in Germany and Ohara in Japan. So the link between technology and science is really very interesting. The resolution limit, many people just gave up, of course. But that guy came with the invention of the so-called confocal microscope, which is a way to better select, simplify, better select the photons which are forming in the image. And it could greatly improve the quality of the image and also in terms of resolution. These are the theoretical value where you see these numbers for the excitation, the detection in fluorescence microscopy. And it works, except that he invented this in the 50s. So, lasers, CCTVs, computer, it worked, not anymore. And the invention was forgotten till the 80s. I don't know where everybody's coming from, but for those who are working in computer sciences, informatics, in fact, the PhD topic of that guy was studying neurons in order to understand. He did not see the neurons with the microscope, so he invented the confocal microscope. Nobody was interested in it, so he worked stochastic lower reinforcement calculator, which is nothing else than the ancestor of convolutional neural networks. Marvin Minsky, one of the father of artificial science. Okay, we have seen this morning beautiful results in fluorescence microscopy. Fluorescence is the kind of queen of the battlefield microscope. It has so many advantages for images, but mostly because there are now hundreds of fluorescent labels and variants which are specific to cellular structures and or cellular functions. So you can label almost anything, optogen, for example, which explains the success of this technique. Also, it has permitted the real breakthrough in resolution. It works, optical nanoscopy works thanks to fluorescence. That was awarded by two Nobel Prizes. The invention of GFP, green fluorescent protein, discovery of GFP, and then modification, which allows to label living organisms, and the super resolution, which was promoted by Eric Metzik and Stefan Kostik. There was more working on single molecule fluorescence. And now we have the state pattern and many variants of this super resolution, except that it utilizes fluorescence. That is a little bit sometimes the drawback. If you do not want, or if you can't use fluorescence, there are not many ways to get nice images. Photofluorescence works very well in many cases, but mostly for vegetal biology, plants, because animal cells are not so photofluorescent. If you switch to femtosecond lasers, powerful, very fast lasers, you can induce optical phenomena like second harmonic generation, third harmonic generations, which gives you information about the structure of what you are observing, because the condition for both second harmonic generation or third harmonic generation are very sensitive to the structure, not to the structure. Not so bad. And for chemistry, it's mostly coherent antistates, Raman microscopy, which works well, which gives you complementary information to second harmonic, for example. The drawback of this technique is the instrumentation. It's really fast detectors, femtosecond lasers, etc. So you have to switch back sometimes to the Pullman microscope. And when you look, there have been, as I said, the resolution was limited. So people really focused on how can I get better images, with better means, without making the diffraction as not possible. At that time, no fluorescence. And many techniques have been invented, like dark field microscopy, optic illumination, right there, etc., etc. Few of them, the phase contrast microscope, which was awarded to Cesar. And the ultra microscope is something very old. The invention is 1906. It was invented to study colloids, and it has been reinvented in fluorescence microscope in the 19th under the name of selective plane illumination microscopy or light sheet microscopy. Really the basic was. If you look at this, they are characterized by sub-control of the illumination, a certain comprehension of the light-specific interaction figure, but they are two. They have no direct 3D sensor. Your eye is a 2D vector. So all these microscopes work with the very basics of optics. So ray optics, the simple ray optics can explain the image formation. So get back to the basics if you have a base, focal points, just ray trace. So if you go through the middle, if you are parallel, passive point, passive point, parallel, and quantify magnification. That's theory. Works. That explains the microscope. This is a kind of microscope everybody should have at one time. The so-called 160 millimeter microscope, which is the low-cost model. Modern microscopes work a little bit differently, in the sense that they are called infinity microscope. In the sense, it works like you have an objective which rejects major. Then you have a supplemental lens. Or the trick is simply if you want to insert optics features, whatever you want, it's always better in optics to which is not the case in the 160. And nowadays, all the modern research microscopes, there are which helps a lot for designing new microscopes. Okay. It works. In fact, it does not work so well. see the reason. An example. In fact, when it's well adjusted, so-called Köhler illumination, that was invented in the 19th century. If you take an object, you can ray trace using the simple the image of your object. So here on the retina, you have intermediate images. The trick is, in reality, you have a transmission microscope, so somewhere source. So mathematically speaking, you can imagine that these rays, they continue. And they come from different points of the source. That's so that you form an image of a sample, but rays which come from the source and following the same path that come from the same point of the source, so you do not focus the source. Okay, you have a diaphragm. So at the same time, you take care that rays coming from one point of the source, they are not focused. So now usually it's focused here. Of down. So that's supposed here, so you don't have an image of your source. That is the trick of the Köhler illumination. It's not so important. When it's well adjusted, it should give you the best images. This is the kind of image you get when you have single cells. In fact, there is an image there. It has a 1% contrast. So you don't see, but it's there. Why is it like that? You have to imagine that here, but here we put a sample which is microscopic. Here we have a very powerful source. That source sends so much light that you are just is full of light. So it's a contrast problem. It's not an image recognition. It's a contrast problem. The proof is, so I take the image, right image processor, so it's a bit dirty. Look, there is something here, and you see some structure here. Remember this what we see. There was something here, except that the contrast is dirty. So the trick is proving the contrast, and historically this has been done by markers. And this is a very famous image from some everyone has heard about it this morning. It was so-called Golgi staining, which are I remember when it's set up. Some type. It was working, except that at that time, all kinds of markers were had. Basically, they were killing the cells. It's good to see morphology. Not so good to study. So, very rapidly. In fact, there's no real paper inventing this. Many people use it. If the problem is that the light coming from the source, just try to suppress the light coming from the source. And this gave birth to the so-called dark field microscope. The trick is using white light and a special annular filter so that your objective does not capture light when there is no sample. When there is a sample, then something occurs, some of the rays are diffracted. And they enter the objective and they can form an image. That microscope is very interesting because it shows that the pure ray tracing cannot form an image. It's diffraction which makes images. Because here we have no samples, so no diffraction, so no rays enter the objective, so there is no image. So the diffraction theory of image formation is okay, dark field microscopy is well known. very easy to implement. Here is a radio line. And if you look at the image, and this is a wide field image, this is a dark field. You can see that and you can also make a colored dark field by select. See that here we have some picture that can be. So we have now a contrast which allows to see small structures. The problem is obviously what is the real image of this? In fact, we have the same sample, 3 different illuminations, 3 different images. So even if one has to simply draw shapes, it's not very clear. It's very easy to recognize dark field microscopy image whenever you have an image where it's black. No sample black and light, where there is a sample here diameter. Reinberg, he came from concept, and then one of the very big reasons, which is often forgotten, of fluorescence microscopy, it's a dark field. You have no light, you have light when you shine citation light, and you have no film. So that's why, for example, single molecule tracking is possible in fluorescence microscopy, because it's much easier to detect a little bit of light on a dark background than a small change when you have high intensity. At that time, everything was done by hand. And Reinberg used another property of your eye. The human eye is not good in high intensity levels, but it's very good in detecting low light, stars. The human eye is also very good at distinguishing colors. So he just modified the previous segment and added colors. So the central rays, they are not blocked, they are colored here in green, while the annular rays are colored differently in red. So obviously we understand we will have a specimen which will appear red. What is diffracted by the specimen appears red. And when there is no specimen, we have no dark field, green field. And detecting slight changes in color, the eye is colored. There have been many Reinberg filters. You can imagine whatever you want. And for example, here is a small animal observed in white field. In dark field, we see different things. It's better contrasted side. And here we have a Reinberg filter. So if you are used to Reinberg filters, it's quite easy to realize that the central disk was blue. There is no sample. And the annular ring in that case was red. And in fact, it is highlighting small parts of the samples when where there is basically blood, for instance. So that's the other name of the Reinberg technique. It's called optical staining. But colors in a sample by pure optical waves, no dyes. Another trick which was discovered at the very beginning of microscopy, it's oblique illumination. In fact, if you look at old and all the old microscopy were using oblique illumination for the invention of condensers. Here the trick is simply, again, to modify the annular filter to take only one side. So it's similar, you have non-diffracted rays. In oblique illumination, some of them can enter, and what is diffracted by the specimen, so it's not fluorescent. what is diffracted by the sample will enter the objective and contribute to image recognition. And this is the kind of image you get. This is the image I've shown you previously. By image processing, you see something. Here we clearly see sample. And here is another sample. It's a little bit better faster, but with oblique illumination, it's much better. But there is a false trick. In principle, all of you should see this is negative steps. Concave or convex. And that's the range. There is no relief in this picture. This transmission microscope. Why do you see this as a kind of pattern? Basically, we are and light is coming time. So when you see such a structure, you interpret it as light coming from the top, and you see shadow here, like as and combust. Just how this looks. So it's a kind of artificial. Yes. Simply because it's so it works. It's very efficient to detect, but you have to be careful with the interpretation of the image. It has been improved quite recently by some docs. And again, of oblique illumination, here you see the mask, which is a condenser. But the condenser introduced not a zero bracket, but thanks to its fusion with brackets. So he studied the brains this, which are quite different. And by dating this, and here in this experiment, and much was able to see rather thin slices. Interesting. As far as I know, it's so manufacturing selling top-spectrum contrast add-on for microscopes. It works very well in infrared because the slices are most transparent in infrared. Hoffman had a different idea, quite similar, but different idea, in the sense that up to now, we are playing with illumination, not at detection. So Hoffman combined the illumination with a filter, a modulator, placed in the back of the plane of the objective, which historically was at times so transparent, weakly absorbent, and more absorbent. If you look at the canary illumination, you understand that the rays coming from the source are parallel with the objective, and they will cross here. Focus here, so it's slightly absorbent. But now we understand that some rays which are diffracted will go there, some rays which are diffracted will go there, and they will experience very different. And this gives nice contrasts, which are, it's the first technique, which is a semi-quantitative, which permits a semi-quantitative interpretation of what you observe. The ray labels, they are now directly linked to the local scope, the local optical scope. If you sample TVX rays towards the strongly absorbing zone, the sample almost does not deviate or very slightly. The sample deflects right, it's less absorbent, more white. So now we have a direct link with the intensity, the locals. The images are quite easy to recognize because now we are not on the white screen. It's not a dark field, it's a gray field. There is no sample, it's exactly absolute, so it's gray. Wherever you have a sample, in some places it's more luminous parts or darker parts. Here it's the white lights in terms of color. If you know, it's because it's an alternance of dark features. The light is sometimes sent to the right. It's okay, up to now we have used only radius. Interference optics, know what it means. Basically, fields, they are in phase, and if they are in phase, they add up. They are in position subtract. And if they are inclination, and compute match differences and create interferences. In white light, the phenomenon is very nice. Monocolor, you have fringes. White light, you have colors, fringes, beautiful, very characteristic colors. Later, the most famous bubbles. For example, it's used to detect stress, transparent plastics, like that, because with stress induces difference in the index of function, so difference features. So that's the scale, but you can do it also by that's the so-called phase contrast microscopy, which was invented by the trick is, let's start with an annular illumination. This is more or less what happens. And then here we have the ways of originating source for computing. And what he discovered was that at the cellular level, more or less one cell eats more or less lambda over 4 path difference. Okay, lambda over 4 is not enough, it's not in contrast. If I add another lambda over 4, I will have lambda over 2. Lambda over 2, I am so destructive images. So you just add, these are the ways which form the images. So you just add an annular plate, phase plate, which will dephase rays coming directly from the source. But the other rays, diffracted rays, they will not see this phase plate. And when doing so, you get beautiful contrast. Again, it's a gray background. So where there is no cells, it's gray because it's lambda over 4. And when you add lambda over 4 plus another lambda over 4, your cells appear darker. And at some places, the phase contrast. He got the Nobel Prize because, in fact, that was the very first microscope able to study living cells with details without markers. For example, the very first movement of chromosome separation was done using this. You can add lambda over 4, you can of course subtract, so it's positive phase contrast or negative phase contrast, and you have a very different image, same cells. Here you highlight the global shape of the cell, while here you highlight the very small structures which are highly different. This again questions the interpretation of the image. Recently, it has been improved again because one of the drawbacks is we see these rings have no biological it's an optical phenomenon. So to its diffraction, and very recently was proposed to improve by changing the classical faceplate to so-called apodized faceplate, which improve a lot the quality of images. That is for you. Other phenomenon which we can use is polarization. So light is we can use polarized microscopy when uses the fact that you can linearly polarize and use linearly polarized light, meaning that the electric vector oscillates. You can be totally not polarized, random, and all intermediate states with similar polarization. It's also linked to the fact that it's coherent or non-coherent. And it's polychromatic. So this was not this light was not used until now. So you can see it like this kind of grids. First vertical polarizer selects the sheets. Polarized vertically. The second is sometimes nothing close. But if you cut something out, and this is the basic. What happens in real life when you drive? If I would be in charge of driving safety, and make the experiment when you have reflection on the windshield. It is polarized, then you cannot see through the windshield because of the reflection. When you wear polarized glasses, you can see through the car, which is in front. So you can see through the car. And this is the basic of script. It seems like that. You have the polarizers and you have liquid crystals. They are somewhat twisted lattice. So when you apply an electric voltage, it twists and it guides light. So light goes through, normally does not second one, but if it's guided, twisted result. Basically, microscopy, we do exactly the same, except that we do not control this. We try to measure what happens in polarizers. So the polarized microscope, the polarizer at the input, the polarizer at the input. But that the idea, they some changes, they what you measure are so-called polarization states and birefringence. And this is the kind of image. So as I told you, it's made in white light, and because change the light fields changes with the wavelength, you again create these nice interference colors. Often it means microscopic image. To recognize a polarization microscope, it's very easy. These are those microscopes where a circular stage is used. It's always a circular stage, except in polarizing microscope. If you see this, one measures very easily so-called extension or polarization ratio, birefringence effects, and in fact, optical path differences. That's a little bit more difficult, but it's rather easy to understand. You need to induce changes, and you need to induce different changes on the different polarization. So birefringence, for example, it's a very famous, very classical calcium experiment. If you look through calcium crystals to images, It works very well also in reflection in metallography because metals reflect light very strongly. And it has been completely tabulated in the so-called Michelet birefringence chart. When you are trained, you recognize these colors. If you know the thickness of your section, so petrography, metallography, stuff, it's very easy. And you, from the color, can measure the difference. So the birefringence. And for example, for crystals, it's a characteristic of the chemical species. Of course, the trick, you must know thickness of the cell. If you start to slice cells, you are not living anymore. And there is a big drawback. When the optical path difference is very small, in fact, you have gray labels. Your eye is not the first distinguishing gray label. It's good colors, but not gray labels. So it was not used for biology, almost not used for biology, because in biology, at the cellular scale, you see almost. But the instrument has been greatly improved by the group of at the Marine Lab. They developed many fancy microscopes. And the so-called polscope is very interesting. It's nothing else than a polarization microscope in which more optical elements have been added, polarizers, but also variable targets. And they are all on a rotating stage. And basically, by taking many images, you are able to fully reconstruct in 3D the direction of the birefringence, so-called AC polscope. And here you see what you see here are the microtubules. So microtubules, you can see them, even if they are extremely small, it's a few dozens, a few tenths of nanometers. But they are highly birefringent. And interesting is the coding here is an angle in space. So in fact, this is the page with the color telling you this microtubule is going out of the screen or behind. So it becomes now something which is much better integrated. We have the 3D, which is part. And the second part was solved very recently. This gray band, the Michelet chart, where you cannot measure the polarization effects. It's from 2015. And the trick is almost so easy. One wonders before. In fact, they used white light, but with polarization which is dependent on the wavelength. In the regular polarized microscope, the polarization stays the same for the white light. Here, they coded polarization dependent on the wavelengths. This beautiful color image, where originally the birefringence is very weak. Here we are the diameter, again, some bonus very small levels. Here, these are the myelin fibers without any staining directly under microscope. So then, obviously, why not combine it? That was an idea from Lomarsky originally. So combining polarization and phase contrast. So this gave birth to a differential phase contrast microscope. It looks a little bit like a polarization microscope because you have polarizers, but you have optical elements which split your beams. Here, the blue and the red are the two orthogonal polarization, and then recombine and then analyze. So it's a polarization, except that it's not like that. And we will play. You see here, light is separated and perfectly white. All the images I took off the website I will give again. It's not because it's on a website, even from the manufacturer website that you will find very strange things. So for example, these are the drawings they gave for the image formation in the last. If you look at this base going from the left, that is negative index material, which is not the reason. So obviously this explanation is left is slightly different. Not but anyway, just to be careful sometimes. Here is what happens at the cellular level. Your two rays are out of the cell. In fact, they will be recombined and blocked. If the two rays go through the cell, they will experience phase shift, not the same phase shift. So they will be recombined and blocked. But here, when you are on the edge, one ray goes through the cell, the other one is out of the cell. So they experience different phase change. So they are recombined into an elliptical polarization, which means some of the light. So if you take an image, it looks like this. And here, if you cross, you can measure its gray, and it's whiter, darker, gray in the middle, mirror, dark, and gray. And this is nothing else than a derivative of the optical path. Computers are very good at integrating this kind of instrument. Just like that. If, again, your setup is very carefully aligned, and because, of course, this quantity, so-called bias and lateral shear, you see, these are the images from the same sample, simply changing the distance between two rays and the phase change tolerated with the result. So when it's like that, it works. It's like that. So to compare phase contrast and differential difference phase contrast, interesting thing, you have the suppression of absolute power. And you get a absolute contrast also. It's gray, and it's, but it's artificial. It's just a gray little tone. But it's extremely efficient at structures. So another example in cells. Everything in the cell. Up to now, everything was 2D. So as I said, everything in microscopy, your sensor, your eye, everything is 2D. So how do we switch now to 3D? There are two techniques. The first one is simply optical section. In fact, any modern microscope is an integral computer. So you can use the control computer for the precision system. Most of the time, you just control the computer. So you take images and focus. And the computer from this called optical section. The computer is able to reconstruct the image. The second technique, which we use, second part, is so-called topography, intensity tomography. This is the simplest case you can imagine. You see that even that you can make the reconstruction by hand. If you have an opaque sphere, the profile you measure is this. So now if you change the angle of same profile, because it's a straight line. But you have many different points of view of the same object. The trick in the tomography, you can reconstruct this by hand. It's a very nice experiment for it. Because of the back projection theorem tells you that you can reconstruct a sphere from rectangles. You just take your profile and you dilute it. And plastic sheets and glue them. And so now if I add a second view, I already have a square. If I add one, this is nothing else than a computer, X-ray computing tool. But it works. It has been done, of course. Microscopy. Okay. Of course, the difficulty is to have this guy rotating the microscope objective. You understand that it's not a very easy trick, but it works. Usually, people use microcapillary tubes, and you grow your cells directly in microcapillary tubes, and you can rotate your microcapillary tube. But optical gel to have a better contact, and then because it's a tomography, it's semi-transparent, for it to pass here. Why not combine all these options? You can do this. For example, here you have phase contrast. You have the materials which are stained in that blue. Here it works, except that there is a kind of Dr. Jekyll and Mr. Hyde when you want to do 3D. It works more or less in 2D, but in 3D, the trick is the following. When you make optical sectioning in fluorescence, the underlying hypothesis is you observe fluorescence. You cannot observe the sample. You observe the fluorophores you have put in the sample. So to reconstruct and to add up the hypothesis, hidden is your sample is homogeneous. But if you see this, your sample is not optical. And this was highlighted by this image. It's quite old, but very interesting. It's a backscattering confocal microscope. So that's not the most important thing. The trick is we have a certain knowledge of what is this. And the cover slip gives a very nice, powerful signal. Here we have cells. Are cells. They collapse. The trick is here we have the glass slide. So we have a physical argument to say the glass slide should look like the console. It's not the case. First, it seems to completely in some cases, and there it's calculated. And that is because of the cells. So the cells are optically active. And if you don't measure the glass slides as flat, with a 6 micrometer difference, largest oscillations. 6 micrometer, 6 micrometer, when if it turns to have a resolution of 2 micrometer, there is a problem when you construct something. So the image of the specimen is therefore by the specimen itself. So to conclude, this is fine. When you consider intensity imaging microscope, you have a very large variety of imaging modes. A colleague of mine was complaining that his students, they were looking for the good dye for the cell membrane to measure the cell diameter. The confocal, just TLC. So don't forget the old techniques, the message. But the contrast is difficult to predict. Resolution is limited, except for fluorescence, where fluorescence like nanoscopy used to be super resolution techniques is a reality. 3D imaging is possible, but as I just said before, be careful when you sum the two slices. See the second part, how we can. If you want to go a bit further, most of the illustration from this site has been shared, and all the big fours, Icon, Manutech-SLEIGHT and size, they have a variant of this original site, so sometimes more interesting things. So I just show this one. Where they are very nice now. For example, you have Java applets, you can with TICH, the bias and the share to see how the image will change, and it's very nice to understand how this classical microscopes style. Right. Exactly. And
Thank you for your talk. Actually, I just want to ask one question. In this slide number 25, when you were of my model issues, 25, 25. Yeah, I can understand this last. Showing it here. Yeah.
And now it's not, these are examples of filters.
Yeah.
You can design whatever you want.
No, I'm just saying in the middle one, you are saying that the diagonal star, the middle one.
This is dark field, in fact. This is the same sample observed here in wide field microscopy, classical microscopy. Here it is with the dark field microscope.
Okay, so those filters are not corresponding.
No. These are just examples of filters, and these are examples of no, but they are not related.
Okay. Exactly, I got it. Yeah. Thank you.
Another good question. How are you dealing with this?
That's a very good question. Somebody who knows about electronics. In fact, we have no missing image.
No missing.
Yeah, because it's a rotating capillary. So contrary to transmission electron microscopy, where you can tilt the fine rectangle without missing image. Can rotate.
So your sample is a needle.
The sample is embedded within the microcapillary. And you can rotate 360 degrees. In fact, it works, but ensuring pure protection. And the micro is very submicro is very expensive. So there's lots of interest afterwards. Correctly. Then correct.
Everybody wants coffee. We gave you meeting here in 15 minutes. 14:45.
Shall we start? Thanks again. In here. So in the second part of the talk, we will switch to quantitative imaging, basically tomographic microscopy. So, okay, just from the previous talk, some control of the illumination, a certain comprehension of the light specimen, interaction phenomenon, and 2D. 2D, no choice, all the sensors are 2D. But we will see that if we do this a little bit better, we can go much, much, much further. First, we can measure phase now. Thanks to the invention of holography, there are three main variants now: Gabor holography, phase stepping holography, and off-axis holography. And recently, we have the development of so-called wavefront analyzers. So we can measure not only the intensity of light, but also the phase, amplitude and phase of the diffraction field. Principle of holography, it's very simple, in fact. It's just a modulation. You have a reference signal, which is modulated when recording and mixed with the wave I want to analyze. The sensor is an intensity sensor, but in fact, you have several terms. And here is what is of interest. So the trick is we have a modulation. It's exactly like a frequency modulation for radio. We have to demodulate. So how can we extract this from this, which is recorded? Denis Gabor got the Nobel Prize in Physics for the invention of the holographic method. The interesting thing is it was invented for electron microscopy, not for optics. But now it's used in optics. So the simplest method to demodulate is simply to put the reference wave angularly shifted. It creates a periodic modulation. And the periodic modulation in the image phase, where we have the fringes, translates into shifting the orders when you take the Fourier transform. So we just take our hologram, which is everything here. If we have an inclined reference wave, we Fourier transform it, and the zero order object between are spatially selected. We just cut. Take this and we have the amplitude and the phase. The Fourier transform of the amplitude and the phase. So you Fourier transform again to a nice image. So phase microscopy, you measure phase differences. They are proportional to the optical path difference. So that is the equation. The trick is just here. It's an integral of variations of the optical index and thickness variations. No way to admit this because it's an integral. So when you go through the cell, you project something which is integrated the direction of propagation. Anyway, you can make many interesting things. And one of the main advantages of the techniques, it's very low level light. So you can have beautiful movies. Here it's over 72 hours, but on the phase holographic imaging site, they have movies of cell cultures over weeks, which is something you can't do, for example, in France. Here are other examples. This was supposed to be anyway. It's not limited by the photon budget because we use lasers. So if we want to go extremely fast, we can. This is supposed to be a move of vibrating red blood cells, and they made beautiful experiments by measuring the vibrational modes, putting this into a optical. And they had the mechanical model of the red blood cell. You can follow things which are being surface. this was supposed to be set up to this purpose. This is interesting to me, as far as I know. So, it's the sole case where an optical measurement has been directly linked to a biological quantity from the face. This is measuring the so-called neuronal respiration. When the electric impulse propagates along the neuron, you have changes in the molarity, but these are ions. So the neuron pumps or expels water to compensate, which means its optical thickness changes a little bit. When I say a little bit, it's a few nanometers optical thickness change. And in this paper, they were able to link the GABA current directly to the face they measure. Here you have the experiments. So they did a real actual experiment where they measure the current. This is the face, and this is a predicted current at time. This equation. There are a few terms which have to be calculated. You have an optical measurement of an ion flux. The good news is holographic microscopes are available. Manutech makes high resolution ones. Phase holographic imaging now has a small model which you can directly put into an incubator, so you can set movies about things. Cell culture. TESCAN is a more recent development, but it's also different. And you have the so-called wavefront analyzers, physics, which is a French very active in the domain. That one has the advantage that it's like a normal camera, which you put microscope button, like the system. Okay, so now tomography, same trick that previously, except that instead of starting from intensity image, you start from phase image, and by back projection, you can actually continue it's in the area. Same trick, and it was embedded in the microscope. Take 3D cell and the interior. Except I forgot to emphasize. Just there is dark spots, neglecting diffraction. And this is quite paradoxical because you neglect diffraction, which occurs small scale, microscope made to observe small samples. So if you don't neglect diffraction, you come to support different general. It has many different names in literature. Just to recall the principle, everything starts from the unit spread principle. So, mathematically speaking, the propagation can be interpreted like that. Each point of hypothetical mathematical surface is the siege of what's secondary disturbance, giving rise to spherical waves, and the envelope constitutes the next waveform. Okay, so plane wave diffraction, let's play. This is a very classical experience. So if you set the plane wave to the hole, it gets very now, interesting thing is mathematically there is a continuum. Plane waves and spherical are fully equivalent. It's very easy to understand. If I open the ball, look, it's reinforced here, it's flatter. If I go there, it's still circular, but it's reinforced. And it's logical because if I open the particle entirely in, there is no hole, so I should have plane wave. So there is really a continuous transformation from plane wave to spherical wave and reciprocal. So the Fresnel-Kirchhoff formula is what translates this into mathematics. So when you want to compute what is diffracted at point P by this aperture, you have to compute this integral. What is important here is to remember that this is a class of so-called strongly oscillating integrals. They are very hard to integrate numerically. Why? It's very easy. K, that's the wave vector, 2 pi over lambda. Lambda 0.51 minutes. But these distances are millimetric centimeter. So you have something which is oscillating, you have to integrate. And it's oscillating thousands, billions. So if you make tiny errors in your integration routine, things fall apart. The good news is we can simplify this. That's the so-called Fraunhofer function. So first, the trick is you put your source at the focal plane of this lens, so you don't send the spherical wave, you send plane waves. And you don't look. Let's look at the thing. That if I have a lens here, parallel rays are focused. And the previous integral skip the thermal calculations and the previous integral transform into this. And I voluntarily write it with C and eta. So but no, it's for my terms. So it's I. So in fact, this is not. So everything can be computed by except that I say that we want to observe 3D objects. So diffraction by 3D object is Fraunhofer, that's 19th century. And curiously, when that wait till 1969 for the seminal paper of the domain, which is entitled Semi-Transparent Object Reconstruction from Holography. That holography was when you take a plane wave and you pass it through the 3D object, okay, it's diffracted. As in the previous case. The trick is if you consider a weakly diffracting object, so mostly transparent. Basically, the diffracted wave is very weak compared to the original plane wave. So basically, first order approximation. And in that case, so-called first-born approximation, these objects is nothing else than the 3D Fourier transform of the index of refraction. So everything is still Fourier transform. So you understand because why this paper was forgotten in 1969, you have to make 3D Fourier transform. You can look at the memory of computers in 69. Then no lasers, or almost no lasers at that time, and no CC. So okay, just forgot. And the revival of the topic was in the 80s, when cameras were available, lasers were available, and computers were more or less working. But basically the trick is there, it's just 3D. So how does it work? A little bit more detailed. This is classical. We will, from this general equation under the first born approximation, add the elasticity. So there is no change in it. It's not generation. So the wave vector, object wave vector are simply the diffracted wave vector. I know how to measure them in topography, minus the incident. I say more or less control the illumination. And then it's a Fourier transform or so-called Beaton calculus. So when you have an object, you illuminate it, it sends waves everywhere. So wave vectors everywhere, space, and it describes the sphere. What I measure on the CCD is a 2D field. But the trick is each 2D spectrum is mapped on this sphere. So I measure 2D spectrum of CCDs, I correctly map them on the sphere, then I shift them because I know the illumination, and in principle, I measure wave vectors from the object. That's the trick from this. So in 2D, these are circles, in 3D, these are cap of spheres. Not the complete sphere, because in transmission, I measure half cap of sphere here, and in reflection, that one. I will only speak about transmission. And because the objectives are technically limited to something like 70 degrees, but this it's a cap of sphere, it's not half sphere. Okay. One is not very used to space. Even in some cases, you can interpret. But it's simply saying that in the spatial domain, we send plane wave and we measure waveforms which are distorted. Fourier space, we send Ki, we measure something on our CCD, we map it on that, and nearby, we are playing VR, basically. And we come back. And here we immediately understand there is a problem with holography, because that is nothing else than holography. One illumination, I detect, I go back to Fourier space, and you realize that in Fourier space, I don't have so much information. But okay, so here is the result of the 3D photos. So the XY cut is nice, but is it really 3D? No, it's fringes. When you are used to it, you can find where the middle of the object is. This is more or less where all the fringes are. But that's cool. So, is it really quantitative? Obviously no. But that is again linked to this problem. The phase is proportional to not to the thickness, not to the index, but the optical path length, which is a mix of both. And it's mixed. We have to find a way to balance. So the first trick is, as previously, I could do it in intensity. It's phase imaging. If I rotate the specimen, I have to rotate back this cap of sphere, so you need to large sphere. And if I take many angles, I will end up with something which is filled. So the advantage is it can be performed with a standard digital holograph microscope. Sample rotation may be difficult. One needs typically 360 meters. And usually to rotate the sample, you have to use microcapillaries, this kind of things. You are limited to rather long working distance, meaning low chemical aperture, so you get an isotropic resolution that's rather low. That is why the preferred tendency now is to use not specimen rotation, but illumination. Illumination rotation is simply synthetic aperture. Meaning that if I change, I control the illumination, I will detect the same direction. The objective has not moved, but minus Ky is different. So, and if I have a numerical aperture, a large numerical aperture, I take many angles, I will feel so-called butterfly. So I have now an extended and field frequency support, so a priori better lateral resolution, something better actually. Previously, we only had one, but we still have something which is common to all the transmission lines. So, meaning that along Z something not so nice. At detection, we are limited by the object. It's as in a regular microscope, except that so the different frequency support we can have by object rotation. And if you look carefully, there is still something missing here along the rotation. By sweeping the illumination, we have this so-called donut. Is missing. Here we have the case in reflection. In reflection, the configuration is different, and we have different frequencies, which are higher frequencies than the so we can combine both. A so-called converter, where we have the central donut and the cup of sphere here. Alternately, can make nation sweeping and a few rotation. And so an important thing is optimizing the illumination. This was a work about previous PhD did, published in 2021. Students from implementing these various things is not so easy. But in the case of transmission, tomography, it's not so difficult because it's simply an extension of digital radiographic microscopy in which we control either the tilting of the spiral chain illumination or we rotate the stuff. So the trick is quite interesting. You have to demodulate the holograms, and the holograms they are all of rather low quality. And in fact, when you see the illumination, it's tilting the angle more and more. So they are not so nice. But anyway, if you recombine everything, you get very nice 3D refraction image. Here we have a numerical optical section of the sample starting at the surface with much better image quality. Just for these two. In fact, so-called aperture technique was a word in physics, but this was regular stuff. But basically, we are doing exactly the same, except that by experience. So here you see numerical reconstruction as a function of the holograms we require. We accumulate information. And you see here the quality of the images improves a lot, of course, but the most spectacular is here. We start from fringes. At the end, we can distinguish potential. It's far from being perfect. It's still of quality is still lower along the optical axis because of the simplicity. This one you still okay, so what is the interest of this? Why do we develop something that is no first? Because we have no first. First, it's natural 3D imaging. This is a diatom which is fully transparent. To give you an idea of the difficulty, this is glass, fully transparent, in water, fully transparent, observed through glass slides, which are fully transparent. You take an aquarium, very clean one, drop glass ball and try to find the glass ball. Okay, you know that's not fruit, but that's. And it's naturally 3D without having to move the stage, thanks to a nice paper from the second interest is, in fact, the index of refraction is a complex quantity. You have the refraction, but you have also the absorption. And here are the granulocytes. And what we discovered on this kind of cells, for example, you can segment the cell, the nucleus, polynucleus, and the envelope, just by coding these two images with different colors. The real part, which is the index, and in red, the imaginary part, which is the absorption. Nucleuses are absorbing but not the envelope, and you see that red is embedded. We can see that it's embedded. This information itself is it's quite nice. It's one of these things are very nice. But it's not there. The thing, for example, that the dyes, because they are colored, in fact, very nice is that the coloration is entirely painted, while the interior color is street. And we have a resolution. We can so high resolution demonstrated in 2009 by Jerome. This is carbon pitch, which is normally electron microscopy, so it's out. And we observe exactly the same zero on the white field microscope. We have the scanning electron microscope. Because it's carbon, it's slightly. And these are the theoretical resolution. 120 units. We have one. This is still slightly better than the optical microscope, which at that time is still kind of reference. Especially that we are working at the learning. But on this kind of image, you have different. The experiment was performed again by colleagues that were it's the 405 nanometer violet. And they get down. It's interesting. It's growing of it's the first time it was observed. That's the first speech. And it's also interesting in the sense that many people that private light was damaging the lights, but in fact it's so right that they from this of it. Okay, so why do we have a better result? Why it's the same optical system? That's the trick of Yeah, the frequency support is the same than a regular transmission microscope. The trick is how these frequencies are transmitted. In fact, in a holography microscope, because we work with coherent imaging, we have a theoretically without transmission, constant transmission about this extension. In a normal transmission microscope, we double extension like here, but the high frequencies are attenuated. While in synthetic aperture microscopy, holographic microscopy, we are able to keep this constant transmission. So the difference is not in the extension, the difference is in the transmission coefficient, which is higher nowadays than the microscope. So this gives the so-called theoretical increased resolution. Good news, if you don't want to set up this, it's commercially available. There are 3 variants. Nanolive has made lower resolution, slightly lower resolution setup than the TomoCube. The interest of this approach is you have huge space here if you want to put tissues or whatever you want. While this is a high resolution setup in 2 microscope objectives. And there is a variant from Firetex. It's super steep. This is so-called wide light tomography, so it's a different approach. It works also very well. If you are interested, just go to their website. And there are now, I would say, half a dozen group or a dozen groups working in the world to further develop the field. If you are interested in possible applications of these techniques, they advertise it very well on their websites. So just go there. There are lots of examples, the application notes, etc. And it seems to work for all the kinds of experiments where you don't want to use fluorescence. There are drawbacks. There are many drawbacks of the technique, which people try to tackle now. Non-isotropic resolution. That's the biggest problem. In fluorescence microscopy, it was good sectional properties. It was the confocal microscope. It's not fully isotropic, but it's much better. Here we have no choice. For example, here is it's another it's a snowdrop problem. That's the sole sample we had in February. Here the XY view and the confocal. So interesting thing is you have 3 different images showing the structures are not the same. But when you go to the Z view, the confocal has nice sectional capabilities, while here you see it looks like the surface evaporates. Okay, and that's still the second biggest problem is speed. If you, I'm teaching in electrical engineering, so if you look at this as a system, in fact, an intensity microscope, whatever the kind, it's a kind of parallel system of treatment of information. You eliminate the sample all angles at the same time. Everything is not parallel in the system. So basically, it's superfast. Tomographic refractive microscopy, you have to control the illumination. So it has to be sequential. And if it is sequential, it means it's automatically much slower than this one. It does other stages, but it's much slower. So how can we first go toward real-time tomographic diffractive microscopy? In fact, fast acquisitions have been performed a long time ago. Here they performed a tomographic system using resonant galvanometric mirror and the 5,000 frames per second camera. Here it was 100 holotomo acquisitions, so 5 images per second, and that was 2011. So in fact, going fast is not a big deal in holography, tomography. We have photons, and nowadays 1,000 100,000 frames per second camera is possible. It's just expensive. The trick is the reconstructions. They are much, much slower. And that's the way usually experiments are thought. You have the acquisition, many data, then you reconstruct, and then you display and you analyze. So the trick we used comes from computer sciences. It's simply like a real-time, multitask real-time operating system where we will attribute three different processes properly synchronized in between with shared memory corresponding to acquisition, reconstruction, and display, meaning that we can start reconstructions before the acquisitions are done. This, thanks to modern graphic card, is not a problem. And that's what we could do at that time, something like 1.4 milliseconds for one hanger, then transfer to the computer. GPU takes 240 seconds for the final 3D boolean transform, so everything is in fact transformed. And then the display is about 1 millisecond. So we could obtain this kind of movies. You see again here with the image, which improves while taking the angles. Interesting part is well, many different frequencies, and you see that the smallest details they appear only when we have the latest angles, the highest NA acquisition videos. So we have the intermediate frequency structure. Numerically construct 0.5 was simulated because the bottleneck now is the transfer from fast cameras computers. So it's still a problem. 5,000 frames per second, megapixels live. There are some systems, but they are expensive. But it's only a technological problem and a financial problem. It's not a fundamental. How can we go to isotropic resolution? That is a big question in the domain because in fact, at the smallest scale, it means people are really hiding many things in the carpet. If you measure an index of refraction of a small droplet, which you see as a rugby balloon and not a football balloon, you may ask me many questions about the validity of the measurements. The object you measure is deformed. What are you measuring? So isotropic resolution imaging is really neglected, and I advocate this strongly. It's not easy, but if you want to make really good measurements, you have to remember that your instrument deforms the object you are observing. Okay, and this was beautifully illustrated by colleagues in Poland, where they are using nanoscribes and micro-nano photopolymerization tools to create artificial cells, where embedded structures with different index of refraction, but very well calibrated. It's calibrated size, it's calibrated in index of refraction. So they call this a 3D printed biological cell phantom. And here is the same phantom observed with system 1, 2, and 3. If you read carefully the paper, you know who is who. Only 2 manufacturers and 1 system from the Polish colleagues. And this is the same object, same artificial cell observed. So you see that, for example, system 3 has been really oriented to perform morphological measurements which are more accurate. The artificial cell is on the glass slide here. It's better than this. But if you look at index, in fact, the constraint they are put to geometrically get back the correct geometrical shape translates into a lower contrast index of refraction. So is this system better than this one? I could say it's better for the shape. It's probably not. That one is better for some diffraction methods. So they adopt a really metrological approach, and that I think is really welcome. But it's still in its. How could we solve this problem? One way is multi-view tomography. The trick is simply, let's take a real tomograph with illumination rotation, and let's make a few rotation. I already showed what it is. You just accumulate the data. So that is the first 2D or so-called butterfly, and then you rotate, and then you add, and then you rotate. So you map your folio space with much more information. At the end, you get you have to imagine this is these two views, and this is okay. The advantage here is compared to tomography with sample rotation, there is sample rotation, but we only need 6 or 8 views because we made tomography with illumination rotation system, and not 100 or 360 views like in the usual tomography by sample rotation. So how did we perform this? We took our regular system and we replaced the stage holding a regular preparation with glass slide, etc. We changed this with a rotating stage. So it's nothing else than a small stepper motor. It's connected to via this cable to an optical fiber. Both the optical fiber is something, but then it's properly adjusted so that when we rotate this, the optical fiber arrives exactly in the middle between both objectives. And now we can perform pictures. And it can be rather good because our intermediate images are from standard holographic microscopy, they are already topographic images, so of better quality. And this is when you succeed. So it's our next problem. It's a vetular pollen grain. It's not national. And here you see the trick. This part is a photopolymer tip which we use to attach pollen to the optical fiber. So we take our nice polymer source, it comes close to the pollen, a little bit of advantage, and then the pollen is attached to the fiber and the again, you see here, blue is coded the index of refraction. So you see it blue, but you don't see it in yellow, which is the absorption, because this is 100% transparent. And if you look carefully, you see that this in yellow is slightly smaller than the blue. In fact, you see on the cut, on that kind, and we found the confirmation of the curvature. The color, the pollen is from the outer wall, which is pure. And here you have a microcrystal rotated with the same tip. And the trick is, at the beginning of the meeting, this is only one tip. And you see the small bubbles, so they are elongated. While this multiple tip, nice, spherical, it's but see, the trick is if you measure the size of an object and you have only one figure, so that you see something which is like that. Volume of the object is wrong. If the volume is wrong, even if the index of refraction is correct, when you try to translate this into so-called, for example, dry mass data, it will be wrong. Okay. Another possible approach is the so-called 4-pi tomography. 4-pi tomography, it's something which is night. If you look at first, 4-pi microscopy was developed in fluorescence, and it was really not working in fluorescence because you have to make an interferometer looking at the object from both sides, and you have to have light interfere. But the coherence length of fluorescence is a few tens of micrometers. So you have to make an interferometer with absolute length of different arms within a few tens of micrometers. And that is easy for astronomy because there are lots of money. Not so easy. But in tomography, it should be much easier. One, because we are making holography, we are using lasers, so we have the coherence. So the trick is, if we illuminate through this objective, we take this objective, that's a regular transmission tomography. Now, we are able to detect what is back reflected. We have a reflection tomography. And we will add this part in the spectrum. And if we now switch symmetric system, in transmission, we will measure the same, but we get the reflection back here, and we will have this. And the trick will be to recombine everything. So here I'm cheating a bit. This is a computation of the components made for 1.45 numerical aperture objectives, which are not so common. They are used in total internal reflection fluorescence microscopy. With 1.4 numerical aperture, unfortunately, this overlap here does not exist anymore, which means we will have a problem. We have, in fact, 4 different experiments, so 2 transmissions, 2 reflections, and we have to fit everything together back. So if we have components which are common, it will be easy, but otherwise it's not so easy. But according to the colleagues in Marseille, then we have a nice XYZ isotropic resolution. So we have started building the experiment. So it starts being nightmarish for experimentalists, but it's rather easy to understand. We are at the intermediary stage where we have 1 transmission, 1 reflection on the same system. So you see the laser, which is here, split the optical fibers. The illumination comes from the top to a tipped mirror, goes to these objectives, the sample is there, detected, coming back, and here you have the reference, and we have the camera here. We have a transmission system, but what is back reflected goes there. Second camera, and we have a second reference. So we have 1 transmission, 1 reflection, and the final step will be to add the same system here. We have the system and the tipped mirror for illumination. To have it, you already have the light which is coming from here, and tipped mirror and send back illumination like this. We will have the reflection camera, and we will have the carrots of but in principle, another interesting thing is in tomography, in fact, in tomography, you acquire all the information which comes from the microscope, amplitude, phase of everything that is refracted. So in principle, all the microscopes I have presented in the first part, you can numerically compute them. If you know how the light goes through, and you have information, amplitude phase, and this is what we have done, we recompute. Here is a simulated dark field image of this pollen. Here is a simulated phase contrast. That one is not so good. Here is a simulated TIC. Here is a simulated Weinberg illumination. We just attribute colors to the information in space. And here is something interesting. It's a simulation of a combined Weinberg microscope, TIC microscope. And if you look at the optical training, they are incompatible. If you have a TIC microscope, you cannot get Weinberg. take time. Microscope, you cannot make the TIC. While numerically, it's possible to improve. That was done during the work of Haeberlé in our group by Nicolas Bernier. We have other papers, theorization papers, and so in principle, we can compute. We have we call it the log of the mean microscope, of course. Have an open one transmission microscope. So what's next? Okay, what's next for the next 10 to 20 years? There are many things to do, because even this is far from being, in fact, everything. Lots of things have been neglected. First, as I've shown that you have the index of refraction, which is index and absorption. In terms of variations of index of refraction, it's not so important over the spectrum. N is a function of the wavelength, but the absorption often is very important. And here you have a so-called spectral energy experiment. So doing tomography, varying the wavelength, the white light laser. And the interesting thing is here. This is an experiment which is routinely performed on blood, but it has been done here on a single red blood scale level. You can distinguish oxygenated and non-oxygenated red blood cells. Thanks this nice curve which has double absorption and that was seen. That was performed by some. So it's spectroscopic microtomography. Microspectrography. That's been performed once. Lots of information, especially from this part. In the commercial implementations of tomography presently, they just neglect absorption. So when you see an IC red blood cell images, microtomograph working with a green mixer on 532, it's called the red blood cell and not the green blood cell. Must absorb green light. But it's just neglected up to now in commercial implementations. Another thing which has not been very widely studied now is optical activity, like for instance, in tomography. Here we made a simplified setup. The funny thing is we mixed potato starches and glass beads. So glass beads, you see them very well in the X and YY components, polymer components. But when you switch to the cross components, you see very well the so-called Maltese cross, the characteristic of private agent samples, potato starch. But the glass beads, they just disappear. Barely see them, but just a residue of refraction. And this experiment has been performed with details by colleagues in Korea. They made measure the optical tensor, or dielectric tensor at optical frequencies. This is a liquid crystal cell, and the arrows are the orientation of the crystals measured thanks to the polarized microtomography. That is, to my knowledge, the most complete experiment. We see with good resolution small samples, but people are interested into investigating model animals, for example. So here is an experiment which has been performed on sea lions with a very simplified setup. It's a lensless holographic system, but it's a battery of LEDs, of small laser drivers to perform tomography along one direction, and it works very well. It has been pushed even much further by a group at the SEA Litsky in Grenoble. So you recognize here the arm where you can change phi angle, or the theta angle is also adjustable, is semi-coherent illumination. And they were able to image cells cultivated in the macrogen and you see the scale. So here we are on something which is 500 micrometer in all directions. So that rather samples, lower resolution, obviously, but something which is rather big and which used for vocabularies or standard samples. Colleagues in Holland, they have combined a large sample approach. So it's tomography with sample rotation, but with low magnification. So it's easier, sample rotation and optical activity by the fusions. And this is a zebrafish tail where the polarization contrast highlights the muscles. The phase contrast is just the face, but the polarization contrast highlights the muscle cells, which are highly biometric. Another domain now very active, it's phase reconstruction. Not phase measurements like in holography, but in many cases, under some assumptions, you can, from intensity only measurements, reconstruct the phase. The main interest is then you can go extremely fast, and here you see the movie where they could perform a tomography, not measuring the phase, but very rapidly measuring the intensity images, and then numerically reconstruct the contrast. You see the bright field image corresponding to this quantitative phase imaging, and fluorescence is superimposed. This is interesting because it simplified the setup. So just LEDs, no lasers, no mirror, fast mirror for scanning. Unfortunately, it works now only on very small samples, very flat. But many groups are working to improve these approaches and try to work on larger samples. Super resolution, that is the big unknown. Super resolution is a reality in fluorescence. But many people are interested in label-free super resolution. There is this book by Vasily Astratov, very interesting book, very big authors by my book. And recently there was a roadmap. The roadmap is in open access also. And phase imaging, it is there. It's between the classic, it's called mainstream, the classical approach, but there are a few links to go to super resolution. The true super resolution is there, so, or in near field approaches like long microscopy. But far field, 3D, unlabeled super resolution, that's still the dream for the biologists, and a nightmare for the biologists. But there is one way in which it is working. Up to now, and most of the time, we are working in so-called low diffraction regime. But if you have other kind of objects, it's not the case anymore. Here, the diffracted wave, when you have such kind of things on silicon, the diffracted, everything is diffracted. Almost everything is diffracted. So you cannot use the first corner approximation. You have to solve this equation. That is the original diffraction equation. And usually what we do is we simply neglect. Here you have a U diffracted, and here you have U diffracted within this triple integral. So to know, we just forget. And you have the elimination. So that's easy to solve. But the people in Marseille at Institut, they are very well advanced on that. And in some cases, simpler cases of the biology, but anyway, it's working. This is a kind of star which is made in polymers deposited on mirror. This is the dark field tomograph image. Nothing. This is this is the dark field regular microscopic image. This is a regular tomographic image. And this is what they measure using advanced reconstruction algorithm. And here they have a true super resolution of lambda over 10. Okay, there are many applications. But anyway, it starts working in the strong diffraction regime. So to conclude, okay, high resolution is possible. It has been demonstrated. 2D, 3D, not exactly, but okay. Unprepared sample. The main difficulty faced when we discuss with people here is they tell us there is too much information because we see, comparing to fluorescence where you see what you have labeled, and we see everything. So there is a new, one has to work on the interpretation of images of this index of refraction distribution. And there are many remaining challenges. And what I hope was properly presented is this. In fact, if you want to make a progress in the domain, you have to combine everything. From physics, you design instruments. These instruments are unconventional imaging. They do not deliver images, they deliver data. You have computer codes to reconstruct images. In some cases, we transform, and then you have nice images, but of course, everybody wants new images. Or in computer science, they ask for simplified acquisitions, which is interesting because then you can go faster. Can go faster, but sometimes you have to redesign and go back to practice. So there is a reason. If you are interested in interdimensional optical imaging. And we made a recent review where if you are interested in tomographic diffraction microscopy, there are more than 300 references. We will have all the basics and the trends of the domain. It's for this year. And that one is open access. So thank you very much.